So now we're going to start working on a topic called convolution. What we've seen so far is that solving differential equations using the current tools that we have can be difficult or even tedious. Probably difficult is not the right word. Tedious is really the best one. However, there are other ways to model a system and get a system's response to an input. And specifically, I'm talking about convolution. So here's the integral for convolution. Y of t, so the response. If you want to find the response at time t, you integrate from 0 to t. Then we have I of t minus tau, where that's the input. S of tau, that's the system impulse response. So this is why we started caring about impulses, response to an impulse. This is where it shows up. If we could find the system impulse response up front, we can apply any input to that, and we can do this integral and determine the output at any given point in time. Now, I will note that in my first, one of my early jobs, I worked for General Motors in the electromotive division, so we made train engines. Most wonderful job I ever had. It was fantastic. I was in the test division, and we would test things. And so back in 1984, they were developing the first computer-controlled locomotives. All right, it was the SD and GP60, and they had all new engines, the 710 engine, and so we had to develop models for these things, all kinds of models, amongst them structural models, so we could model vibration in various components, including within the diesel engines, the structure where they would walk around the train. And how did we do that? Well, we never once generated a differential equation by hand. One of the tools we used was we literally went around with sledgehammers that cost probably 10 grand, but one side of the sledgehammer was for sledging, and the other side had a calibrated load cell. So we didn't try to give a unit impulse input. We just there's a sensor on the back, and the computers would measure the intensity, let's just say, of the impulse, and then they would measure the output and then do a ratio of them to normalize that. But the point is we literally went around the train and banged things with a sledgehammer, and it had to be done very precisely. You couldn't double hit and things like that. And we would measure system impulse responses. So we could use that for figuring out doing torsional vibration models on shafts. Again, structural models for looking at modeling the behavior of the superstructure of the engine. We use this in so many places. So this is where you can see where convolution is relevant. If you can figure out a system's impulse response in some way, and these tools exist, you can measure that and then integrate any input you want against that and figure the output. Fascinating. So there's the basic idea. It is relevant. This is done in the real world. I have done it. But let's look here at this equation. All right. And the equation is strange looking because we have this I of t minus tau. And you kind of got to look at that and go, what does that mean? It is, as opposed to just I of t, you could easily say if it was I of t multiplied, or I of tau, you're integrating against tau to figure out what's happening at time t. So if you just had an I of tau there, you'd say multiply this by that and integrate it, and it'd be easy. But what is this t minus tau nonsense? Okay, that's what we're going to focus on right now. I will just give you the spoiler alert for what it is, and it probably won't mean anything. But what this does is say, take the input, and so let's say we had a plot of the input, and I'll just let that be my hand. And it says, take the input and flip it. Okay, so if you normally had an input, here would be the first input, second input, third, fourth, fifth, as you went through in time. This basically says, take the input like this and flip it at time equals 0. So now here's the first input, the second, the third, the fourth, the fifth. Let me move my hand over so you can see it, okay? So here we have this, we flip it, all right? And then we slide it through like this. So the first input is attacking the impulse response first, and then the second and third, so on and so forth. So that's what we're going to see. I'm saying that in the hope that might help a little bit, because this is a little abstract, but we're going to nail this down. All right. So we want to figure out what I of t minus tau for a tau going from 0 to t. Excuse me. All right. So just to give us some structure, let's consider an input that's 1 plus a ramp. All right. And so here's the input. We have nothing at time equals 0, and then you have a step and a ramp happening at the same time. So the ramp starts from 0. So here's the step. It gives us a 1, and then we ramp up from here. Okay. I picked this so it'd be easier to see as we start to make things happen. So what I told you is we're going to take this, flip it here at time equals 0, and then we're going to be sliding it through. All right. So suppose you wanted to know what is the response at y equals 2, okay, or y at time equals 2. All right. So that says t equals 2 here. You'd be integrating from 0 to 2. So I would need to form I of 2 minus tau. All right. Where here in the integral, tau would go from 0 to 2. All right. So tau goes from 0 to 2, t equals 2. That's what we just said. All right. So if we let tau equal 0, the regular t is fixed at 2. All right. You'd go, okay, 2 minus tau. Tau is 0, so you'd have I at time equal to 2. So we could just go over here. What is it at time equal to 2? Well, it's 3. Okay. So that's tau equals 0. If we let tau equal 1, 2 is fixed, minus the 1. That would give us I at 1. I at 1 is 2. Okay, we'll note that. And for tau equal to 2, you'd have 2 minus 2, so 0, and there it's 1. So let's plot this as a function of this separate time thing. Tau is going from 0 to 2. And now let's look what we get. Here we are. For tau equals 0, we're at 3. For tau equal 1, we're at 2. And tau equal to 2, we're back down to 1. And we could put an equation to this, 3 minus tau. Let's look what happened. What we did is we flipped right at this point here at the origin. So that would be coming up this way. And then we slid it over 2 seconds. So picture, if we flipped this over, we'd have been at 2, here at 1, 2, and then 3 going back. But we slid it forward 2 seconds. Okay? So we did a flip and a slide. All right? So that's what this means. You may still be going, why? Hopefully you can kind of visualize this now, but at least you can see this crazy little equation here, this little phrase. It does a lot. It does a flip and a slide. It's kind of, you never would have thought the math could do that. All right? So this just says what we just said. And if we did this for t equal to 4, you can see, okay, we slide this here, and then we move it out 4 seconds. So that'll put the 1 here at the 4. And then since this is at 45 degrees, that'll be 2, 3, 4, 5. And we could go through this whole process and you'd find what we did here, that'd be the equation. All right. Why do we do this? Okay. Picture, we're going to put this thing here. So now this is the flip and slide against S of tau. And so what we're essentially doing is picture if we had the impulse response in the same plot. Or down here, we have the impulse response along here. Each input, the whole idea of the convolution is that this is the impulse response. the input is basically a continuum of impulses. So we can have each one of these, this continuum of impulses causes one impulse response. And so the idea is then you add them all up. All right. So as the input happens, here was the initial input. It's right here. It's the initial input. After 4 seconds, it's saying, if you were to have a plot here, and I'll just put a little line, you can barely see it, but whatever the impulse is at 4 seconds, that's what this is exciting. Whatever the impulse is at 3.5 seconds, that's where the impulse response is, that's what is exciting. And whatever the impulse response is right at the start, okay, that's what this input with magnitude 5 is exciting. All right, so we're going to add up all of these excitements onto the impulse response. And so the idea is that as this thing goes forward, eventually the impulse response would die down to 0. It's a stable system. And then this, as it moves past the response of the impulse, wouldn't excite anything anymore. And then, so only the stuff that's basically coincides with an impulse causes a response. So we're going to start going over that and seeing how that works. And but this is the first idea that we have to get down, is this sort of flip and slide idea. So we're going to end this video right here, and we'll come back and do some more.